Okay, a very good morning to you all. It gives me a great pleasure to introduce our speaker for today and a very close friend, Dr. Dominic Ong. Dr. Ong is a fellow member of both Engineers Australia and the Institute of Engineers Malaysia. He is a chartered professional engineer and a registered professional engineer. He is also the co-editor-in-chief of Geotechnical Research, which is a journal published by the Institute of Civil Engineers, ICE, UK. He is also an adjunct associate professor at Swinburne University of Technology. Dr. Ong is also an expert member of Technical Committee TC 104, that's Physical Modeling in Geomechanics, and TC 207, which is on soil structure interaction and retaining walls in the ICC MGE. As a soil infrastructure interaction specialist, he has won the American Society of Civil Engineers, that's ASCE, Outstanding with Reviewer Award for the Journal of Waterways, Port, Coastal and Ocean Engineering in 2018 and 2019. He has also received the Institution of Engineers Malaysia Best Technical Paper Award in 2018. Dominic has a particular interest in the field of traditional geotechnical engineering and is a specialist in the underground space technology, soil infrastructure interaction, involving deep excavations, tunneling, pipe jacking, pile foundations, soft soil treatment, field instrumentation, and finite element modeling. Very recently, he has developed greater interest in resource engineering and bioengineering, specializing in granular and clay-based geomechanical characterization, application of binder technology via microbial induced calcite precipitation, geopolymer and biopolymer, as well as payment, recycling and technology. So without further ado, I would like to invite Dominic and request him to start his presentation.
Okay, thank you, Ashish, for the very kind introduction. I've actually shared my screen, so you can actually see the presentation first page of my presentation right there. It's good, and thank you very much to the organizing committee for having me here today to speak to you on characterization of granular geomaterials in soil structure interaction problems. And a very good evening on my side of the world here. I'm actually in Brisbane in Australia, so it's actually 4:10 p.m. now. I believe it's just about turning 12 in Mumbai. So good morning to you in Mumbai, and if there's anyone else listening in from some other parts in India, I'm not sure if you've got a time zone, but a good afternoon to you as well. Today, it's my pleasure to actually share this presentation with you. I have to acknowledge my co-author, Dr. Chu, who was my first PhD student about more than 10 years ago. So in today's presentation, I'll in such a way that it's a learning, it's a process where we actually learn as we develop research that goes more and more complicated. So I'd like to acknowledge, obviously, my first PhD student over there, and the other 4 PhD students who are currently either they've already just graduated, like Frederick, or the ones that are currently doing their PhD. Number 3, Irfan, number 4, Nicholas, and number 5, Xiao Qian. Now I'm at Griffith University. Previously, I was at Swinburne, Malaysia, and Swinburne is another Australian university, the only overseas campus in Malaysia. If you know Professor Bala Subramaniam, he is Emeritus Professor in Griffith University, where I'm currently at, and also Erwin Orr. He is currently my colleague over in Griffith University. So in today's, I rather call it more like a sharing session of what we have actually gone through, how we started, how we the longevity of the project, and how we actually prevail through all the challenges that actually lead us to where we are today. So this research started about a good 12 years ago when I first joined the university in Malaysia. So the outline of presentation as will be as such, I will be presenting and talking about the problem statements and then what motivates us to pursue this kind of a research. It's been 12 years now. Of course, I've got some other research, but this is the particular one that is very close to me. So that's why I feel like I'm sharing this with you. Then I'm going to introduce to you the power law as well as the generalized tangential approach. And then we'll be touching on a bit of characterization of geomaterials, and I will introduce to you and also show you some figures. And if you want to read more detail, you can actually find it in all our publications in AACE journals that I've given you some leads so that you can actually follow through, or you can contact me if you need further details on all these materials presented today. And in particular, I'll be talking about two applications, micro tunneling through pipe jacking method, as well as floating stone column project in Vietnam. So I would like also to share with you how we characterize the granular geomaterial in order to derive some reasonable back analysis. So that we learn from what we have actually done through the project. You would be able to apply it to some other new projects or to some new knowledge that's related to granular geomaterial. I've also contextualized some of these materials for teaching because we're in the uni, and then some of these materials like even as basic as a C dash and phi dash. How do we actually approach this? Do you consider stiff material as not having cohesion? And what about dilation angle for high that? So this kind of thing is that we would like to actually highlight to the students so that they would be able to understand. And also we have some videos. We got discrete element modeling that I'd like to share with you as well, and to help students visualize the direct shear test. So I can show them what's happening to the granular geometry inside the shear box. And then I'll also share with you our ongoing research on granular geomaterials. Just share with you on the what Griffith actually offers us in terms of cloud computing, 3D printing, and various opportunities. Okay, so I will start with the problem statement. So when this particular pipe jacking project was conceived by the contractor and the consultant, of course, with the government, it's actually the very first time that in my hometown in Kuching, East Malaysia, where they are doing a ground project. So it's a very massive project over 10 years. So now we are into phase 2 of this micro tunneling project. Basically, we are installing sewer pipelines to sewer up the city that we do or black water being released into the waterways to protect the environment. So the moment you push the flush button in the toilet, your waste will go down all these sewer pipelines, and they will flow under natural gravity, and then all crisscrossing the city, and then finally it will arrive at the deepest point at the wastewater treatment plant. And at that deepest point, the wastewater treatment plant will be able to pump up all the sewage for processed for processing before it's actually released to the river. So this involves a lot of pipe jacking work underneath the city. And the consultant is actually from Singapore, and they model this after Singapore's own deep tunnel sewage system by CH2M Hill, is American company. And we actually worked with them. At that time, I was with the consultant, and I was to become a faculty member in the university. So it's in between that time. Okay, so the problem that we face once a contractor actually won the job here is that we realize that pipe jacking is usually done in soils. If you were to Google on many pipe jacking projects in this world, they are mainly done in clays, they are mainly done in sands, but there are not many projects actually that actually do it in soft rocks. So this is one of the main issue that we do not have much reference. We do not have much analytical methods to start with at that time. So we are pretty much given a blank piece of paper. And then the second problem there. Sorry, I'm just trying to move this mosaic out of my way so that I can. Ashish, do you know how to move this mosaic out of my own screen? Okay, never mind. I'll just go on. The problem statement number 2, phyllite is predominantly having the RQD of 0. RQD is rock quality designation. So within one core run, you have RQD as 0. So out of 151 meter, out of 206 meter core run coring through this phyllite material, we have 151 meters all recording RQD 0. So as you can see, the bottom right figure right there, you see that they have this rock mass have subvertical fissures, subvertical planes, bedding planes, and then they, as you sink a borehole vertically down, cutting through all these subvertical veins or fissures, then that's where your rock would actually break up, and then you will record RQD as 0. But the issue here also is that, does that mean that your rock mass in the ground has no strength? Okay, because you see that the recorded result is RQD 0. If the rock mass is in compression, confined by the confining stress, okay, do you expect to see this kind of a fissures that open up? So, you know, this gives us another perspective of the strength. So on record, on paper, is RQD 0, but in real life, as you try to tunnel through this kind of material, okay, the answer is that you do not get 0 strength. You have actually quite relatively high strength. So again, whatever that we got on paper is actually not representative of the ground, and this gave the contractor initially a bit of a challenge in characterizing the ground. Okay, so it has a strength representation in this case. Okay, so the problem number 3 is that despite the rocks being highly fractured, like what we mentioned, the tunnels can actually self-stand. So it actually demonstrates clear strength. Okay, but how are we going to quantify the strength of this kind of a material with a lot of RQD 0? Okay, so that is another, you can identify it, you know the problem, but how do you characterize it? How do you give it a value so that you'll be able to at least design for it? Okay, so what I'm going to do here is that just to let you know that this is a pretty much collaborative project between the government, the contractor, the client, and the university. Okay, so we actually, our motivation is actually to ourselves answer those questions that we find that is been issued to us so that we can actually move forward with the project. The motivation here is that this is a typical desert structure in Arizona in the US. But I use this slide because it clearly shows us that for cohesionless material, you can see that you can define a slope to it. For cohesionless material, you would typically use C dash equals to 0. The phi dash is your angle of repose that would represent the strength of the material. But what about that structure right there? It's standing vertically. Okay, so how are you going to define the C dash phi dash to represent the structure that is so strong that is standing vertically as such? So the reason why we want to explore C dash and phi dash is because it's more Coulomb parameters, strength parameters. So it's very commonly used in any software and in any empirical design. So we would like to actually follow through that in defining geomaterials with C dash and phi dash strength. Okay, so in this particular slide here, I just want to introduce to you what we actually how we actually see the difference between a large TBM for rod tunnels and a micro tunneling using a pipe jacking method. So on the left half, you actually see how a TBM would actually penetrate through the ground, and then you would have the lining installed within the tunnel, and through the lining you will have injection of grout to seal up the tail void that actually left behind by the tunnel boring machine. So there's no void at all. There's no issues about gaps, okay, because you have tail void grouting. But on the right half of the figure right there, for pipe jacking, as you can see, you basically have a launch shaft and a receiving shaft where you would lower down your frame, your jacking frame or your jacking station, and then it has some high-powered hydraulic jacks that actually push the segment of a 3-meter length through the ground, and then assisted by the micro tunneling boring machine at the leading the way. So with that method, you are actually very much inclined lubrication, but then again, how effective is your lubrication throughout the entire alignment of your sewer pipeline? Because as you enter a different rock material, you could be into a different leakage because of fissures, because of maybe a fault line, or maybe because of a old you have losses of your lubrication into the all these structures. So in a pipe jacking, you actually use lubricant injected through the segmental pipes, so that you actually would want to reduce the pipe frictional resistance, so that you'll be able to adjust as far as possible up to the limit of your hydraulic jack. So here actually tells us that if you got a ground that is highly fractured or has a lot of fissures, you would have the lubricant escaping into the ground. And if this is so, your jacking pipe does not remain suspended in the overcut tunnel. It would actually be under gravity. It will fall under the base of your tunnel. Okay, and then it will be scraping the bottom of the tunnel. So if this situation prevail, then you would actually generate a much higher jacking force because of the frictional resistance provided by the rough surface of the rock. So these are the differences between the rod tunnels and the micro tunneling method. Okay, and this is also another figure to show you that in some cases, the top right figure, in some cases, the rock can be actually quite intact. Okay, and once you inject lubricant into the overcut tunnel, okay, you would have the entire lubricant being pressurized. They will make the tunnel stay afloat or be suspended in the lubrication, okay, and then you would easily be able to jack your segmental pipes through the distances, and then with minimal jacking resistance. So this is, of course, the top right is the most ideal situation, and the bottom right is where you have lubrication escaping through the fissures. Nowadays, you have the lubricant that would actually gel, that will actually solidify after a certain time. It will become a bit of a gel-like material, and then it will actually plug all the fissures. But then again, this material is very expensive. So the contractor is trying to see if they could actually characterize the ground, and if they identify that this area, this stretch has certain high leakage, then they will use the gel type of a lubricant. Otherwise, they would just use normal bentonite to actually provide the suspension of the pile as much as possible, the suspension of the pipe as much as possible. So in this particular case here, jacking force versus geology. So what you can see, we've got two geologies that types of geology. One is sandstone, and one is phyllite, the material we saw earlier on. So as you can see, this is all the discrete data that was actually plotted to form a continuous data over the distance of jacking. So as you can see, the lubrication use, okay, there's not much of a difference in terms of phyllite or sandstone in a way. Jacking speed, well, it's more or less the same. But if you were to look at jacking forces, okay, you can see that in phyllite, the jacking forces are relatively much smaller than the jacking forces in sandstone. So this figure here shows us that it's very much dependent on the geology type that will give you the kind of variations in terms of your lubrication, in terms of your jacking speed, and in terms of your jacking forces. So we have got all these case studies documented in our papers. I will show you, I'll flash to you the papers so that you can read if you are more interested. But this is just general conceptual work that I'm trying to present to you. So in this jacking force model, we have actually searched through about more than 30 plus analytical solutions to see which is the best force model that we could actually try to implement for our pipe jacking process. So you'll find that, like what I mentioned earlier, a lot of these pipe jacking equations, they are for soils, and then they are for like sand and clays, and not so much for rock. So out of those 30, there's only like about 2 or 3 that are mainly on the rock. So out of those 3, we decided to use the jacking force model by Pele, Bucco, and Kastner to represent our case, simply because it's actually that it actually considers the vertical source stresses acting on your pipe crown as well. So what it means is that in a way, it actually considers effect as well. Sigma EV in the Pele-Bucco equation seems to be the one that would actually give us a reasonable estimate of what we are trying to do. Okay, as you can see here, F is your jacking force. Your coefficient friction is the one that we are going to back analyze to obtain the coefficient of friction for the entire alignment of jacking. Okay, and all these parameters here, like the L and the D's, are all constants that you'll be able to compute. Sigma EV, now what I mentioned, we're interested in this because you want to look into the also the arching effect of the material above the pipe. Because if you would be able to estimate the arching, you of course would be able to help to explain the jacking forces. Because if the upper part of the soil does not arch, okay, you're going to have the full brunt of your vertical pressure pressing onto your pipe. So if you could have the above soil to be able to arch, and you'll be able to, in a way, quantify whether it's actually arching or not, and also to estimate some magnitude to it, you would be able to generate a better calculation for the jacking forces. Okay, this is sigma EV. So as far as this sigma EV is concerned, it actually uses C dash and phi dash. And so this is another reason why I've said earlier on, we want to be able to characterize the C dash and phi dash of the rock. Okay, so sigma EV would basically tell us if it's a positive value, okay, there's some no arching. If it's a 0 or a negative value, it has some significant arching taking place in the upper part of your soil above the crown of your tunnel. So the highly fractured phyllite, what we're going to zoom into now. So if you look at the phyllite tunneling spoils, you can see that they have edges, okay, and then it actually quite you know, it has actually sharp edges, and it's not spherical at all, unlike sand. So if we were to reconstitute the tunneling spoils into our direct shear, how do we actually obtain the equivalent strength parameters? Because bear in mind, like what I mentioned before, we started this project together with the consultant and the contractor and the client at the same time. Okay, so the best we could actually study is the behavior of the materials once it's actually taken out of the ground. So that's why we started with the tunneling spoils. So this project is more towards back analysis, which means the project is running. We cannot stop the client from running the project, but at the same time, we are collecting whatever information or whatever material that we have actually obtained from the site and bring it back to the lab and do a bit of a back analysis or a reverse engineering, at least trying to explain what is actually happening so that we can actually bring new knowledge to the next phase of the project, because this project is going to be more than 10 years. So that is when we decided to go down to site, and as you can see here, the tunneling spoils. The tunnel has actually been chewing up the rock, and it's actually through the bentonite transportation system remove the tunneling spoils and bring it up to the ground surface. So from there, you can see a separation machine right there, a decanting machine right there. And then that will actually separate all the materials, and then they would dump the spoils at the site. And this is where we would actually obtain the tunneling spoils and then bring it back to the lab and then reconstitute into the direct shear box and to shear the material. Okay, so we're going to look in this particular case as case study to see how we actually do the back analysis. So this is sandstone in the as a tunneling spoil, and then you have shale in the middle, and then you have grauwacke. So all are poorly graded and sand-sized tunneling rock spoils. Okay, look at the sphericity versus the angularity of the various materials. So we substitute metal into the shear box, and then we would actually do direct shear tests to obtain the parameters. Then you can actually see here when you try to shear phyllite and as well as the shell, you can see that there's a peak happening to the phyllite material. There's a bit of more interlocking going on. And then you can also see that in shale, there's quite a bit of flat. It does not have a post-peak behavior because it's more like a rock. So you can actually see that there's a distinct behavior in the metal. And another thing is shear stress versus a normal stress plot. After you've done your direct shear, various that having a non-linear behavior. Non-linear behavior actually prevails over the range. So if you've got a non-linear and then you have a more Coulomb parameter, how are we going to do? Okay, this is another result showing that for phyllite, you can see that the non-linearity is actually more obvious. If you were to actually use, not to use a non-linear model, are you going to get the more appropriate parameters? So all these are question mark. So how do we go about doing this? Okay, so as we know that the co-equation requires C dash and phi dash for us to actually derive the parameters. So we have actually explored and we have actually used power law, okay, to its advantage, because we know that power law has been used over the last 40, 50 years to describe geomaterials. And there's also a good collection of literature of telling us what the A and B parameters would be. So the A and B parameters are actually depending on your rock type, okay, and your shear stress and your effective stress. They are both linked to the parameters A and B. So would that be a good way to do it? Okay. If you were to look at this table here in terms of the tabulated results for A and B parameters for the power law, we have got a couple of publications right there. We talk about phyllite, we talk about in case study 2 later on in this seminar. I'll be sharing with you on microtonalite instead. So we have got the A and B parameters that we will recommend. And if you were to look at other authors, they've got their sandstone parameters, A and B, they've got slate, they've got conglomerate. So they have their own sets of values to recommend. So if you were to look at the B parameters especially, you can actually see that there's a bit of a consistency in terms of the B parameters, in terms of the values. So they're all about 0.8, about towards 0.9, some they're about slightly about 0.7. Okay, so we can see that there's a bit of a good correlation in that sense. And that is exactly what we do, because what we do is that we would recommend the A and B parameters, and then not only that, we do back analysis for one pipe jacking drives. If you were to look at all our publications, we actually done it for about more than 10 drives in different geology using the same A and B parameters to consistently obtain good results in terms of the back analysis. So the issue here remains that jacking force models uses the more Coulomb strength parameters, and once you can actually fit some curves to it, how are you going to pick the parameters? So we actually recommend to use the tangential the generalized tangential approach, where you would have to know the depth of your tunnel, and then you would from there work out the confining pressure. And once you know the confining pressure, okay, at that particular instant is where you draw your tangent line cutting through that point where your intercept will give you the equivalent C dash value, and obviously the angle to the horizontal will give you the friction value. So we denoted the C dash with a subscript of T to represent the generalized tangential parameters. With that, we would be able to consistently described or represent the C dash and phi dash in our back analysis. So the power law gives us a bit of a curve fitting exercise, okay, to have non-linearity. And then the second method we use is the generalized tangential approach, based it on your depth of your tunnel, confining pressure, and then from your x-axis, your confining pressure, find that particular point on your curve that you have just defined using power law, and then fit a tangent to that, and from there you'll be able to get your C dash T, and then you'll also be able to get your phi dash T. So if you were to rearrange the equation, you'll be able to get C dash T and phi dash T in terms of your power law parameters A and B. So with that, we would be able to find a very consistent way to characterize various type of geological occurrences that encounter on site, and to continue using Pele-Bucco equation to do the back analysis. Okay, so this is some of the parameters just to show you for test 1 and test 2, some parameters. And what we have actually done is that we have done some back analysis. Okay, you can actually find it on in our paper in Journal of Geotech and Geoenvironmental Engineering. That was published about 5 years ago. Okay, we actually talk about the lubrication that was actually injected into the ground. Okay, we look into the jacking forces, and then we back analyze the coefficient of friction. And if the coefficient of friction is less than 0.1, it shows that the whole pipeline is actually well lubricated, as you can see on the figure at the top middle part of the slide there, that one there, the jacking pipe. Okay, so on the other hand, if you have a coefficient of friction of 0.783 in this particular case here for shell, which is much greater than 0.3, is shown ineffective lubrication. So that's how we actually coin these two figures. One is like almost like a watertight, and it's actually represented by phyllite, and then the other one is actually on other geology that has fissures that will allow the losses of lubricant through them. So in this case, your sigma EV gives us a positive value, and it shows that there's a reduced arching. So if you were to look on the left hand side here, sigma EV for phyllite is actually minus 14.4, which shows that because it's a negative value, it shows that there's a sigma arching happening, and that explains consistently why the jacking forces for phyllite is much lower as compared to the jacking forces for other types of materials. So again, what this phyllite is telling us is that even though we have RQD 0, but as a rock mass under confining pressure, the fissures are actually they are not open up. They actually provide kind of a watertight situation where your does not get lost. So time where you have issue is that you try to sink a borehole and try to extract the sample, and you get out 0. So from there, we already roughly know that this is happening, and this is how we prove it. So then it gives us another idea. Let's do in situ testing next time to characterize rock strength instead of sinking boreholes to extract it. So that was the recommendation for the next phase of the project. The client and the contractor was very happy because we managed to actually do pressure meter tests. Now, then you will ask me, okay, why pressure meter test? Because pressure meter test is usually for clays, but now we are doing it on soft rock. So this is where it has a bit of a research agenda. And I've got a PhD student, student number 2, Frederick, who has actually just completed his PhD, and that's where he used using pressure meter to actually interpret rock mass. So how we do it is that we couple together. It's like more like a couple analysis together with finite element, so that we would continue to develop the yield stress where the physical pressure meter could not achieve, and we use finite element to actually model to failure. So from there, we'll be able to obtain the equivalent C dash and phi dash again. Here is that to keep on obtaining the equivalent C dash and phi dash to fit into the Pele-Buchor equation, and true enough, we can reliably do that. So we have got a couple of papers in AACE also, and also TUST, tunneling in underground space technology. We've got a couple of papers in there that will be published soon. That is where we talk about how we do pressure meter testing. So as you can see, we started with reconstitution of the sample. We sculpt the sample based on ASTM. ASTM allows us to sculpt the sample. That's how we can actually fit sand size tunneling spores into the direct shear box test. From there, we have advanced on to pressure meter testing. And from pressure meter testing, now we are moving into discrete element modeling and things like that. So from our journey, we have found that the influence of surrounding geology is tremendous on a lot of soil structure interaction work. It influences the equivalent soil strength. So of course, I believe that some of you may have other methods to how to characterize your sample, but to us, using the power law and then the tangentialized the generalized tangential approach has been very reliable to us, and we have been continue to develop that along the way. So with the Pele-Buchor equation, that will be able to help us to predict whether arching actually exists above the pipe crown, because all this are to be knowledge to the contractor, so that the whole agenda is to lower the jacking forces so that they do not have to pump a lot of lubrication into the pipeline, and that will actually save them money. So can you imagine if you got 3 shafts over there and you can omit 1 shaft and to pipe jack all the way from shaft 1 to shaft 3, you basically save costs on constructing shaft number 2. Okay, you have to do it very well, because if your pipe resistance exceed your hydraulic jack capacity, that's where the problem will come. So if you do not predict it well, okay, then your hydraulic jacks have achieved the maximum capacity, and your pipeline hasn't gone out to the retrieval shaft. That's where the problem is. Then you have to come with a rescue shaft to sink and to rescue your tunnel boring machine. Okay, so that is a double-edged sword. You have to be very confident with what you do. So the client and the contractor allows us to do quite a bit of research and then feedback the research, and then they would actually execute it on site. So that gives us a very good collaboration between university and industry. Okay, so I'm going to release this poll here. That slide just remind me. So if you do not mind, I'm just going to release this poll to seek a bit of feedback. Okay, so I believe it has been released, the poll. I hope you can actually see that.
Not yet. I think Dominic, no, not yet.
Not yet. Okay.
Perhaps you're sharing your PPT. Is that the reason? Or you can share the window.
Okay. Okay, I've just opened the poll. Can you see it now?
Yes, visible.
Okay, all right. So you could actually make an attempt on that while I ready to move on with my slides. Okay. So case study 1 on micro tunneling. I'm going to lead you into case study 2 here, where again to try to show the effectiveness of the power law and also the generalized tangential approach in serving our needs of characterizing C dash and phi dash. I will also present to you these floating stone columns, okay, in soft clays, and how we characterize the stone column materials using exactly the same way of how we characterize using the tunnel spoils. Okay, and I have to acknowledge my previous university, Swin. We collaborated with NUS. That's where actually I graduated from, together with Ashish. And then Prof. Leong was actually part of the research team, and Keller was the one that actually support this back analysis again. So for this particular project in Vietnam, as you can see, the soft clay consists of about the first 12 meters. It has very low SPT, less than 5. Okay, and then as you can see, typically of soft clays, you have content that is between 60 and 80%. With a plasticity index of in excess of 20 and close to about 30%. So the initial project requires a PAL foundation. PAL foundation would actually go all the way down to, if you were to look at that, all the way down to probably 55 meters. Okay, so that's when Keller came onto the discussion with the clients and the project team, and they proposed to improve the ground using floating stone columns, where the stone columns would be obviously floating in the soft clay, and with the toe probably sitting at the stiff sandy clay and the soft clay interface. So obviously, when Keller has decided to do this scheme, they invited NUS and NUS Prof. Leong, and invited myself to actually participate in this back analysis to help Keller document the entire construction process and to also verify their design. So that's how all this work started. Okay, so the gravel at site for the stone columns, as you can see, they vary from about 20 to about 50 millimeters, and it's actually microtonalite. Microtonalite is granite. Okay. So with that, we brought it to the lab. We actually crushed the gravels down. Actually, it's like gravel towards cobbles fraction. So we actually crush it down to sand-sized particles, as you can see there, so that we will be able to them. Like what I mentioned, ASTM provides you with the opportunity to sculpt your sample, and then you will be able to place them in your shear box, and then you can actually do the shearing test. So that's how we actually do it, taking modeling after the tunneling project. So in this particular case here, you can see that there are various configurations that Keller wanted to test on site, and you have test 1, you have 2, you have test 3. I think we have about 4 tests, and all of these tests we use the same technique, using the power law technique, and as well as using the generalized tangential approach technique to characterize the granular material. Okay, we have got this paper published in 2018, where we do the 3D modeling as well as the back analysis in trying to get the pulse soil response. Okay, so I will slowly go into the slight details of this paper. So as we know, the stone column materials are individual or isolated aggregates, and they are actually compacted using a vibro. Okay, and the vibro a lot of compaction energy to compact the granular material to form the stone columns. So in this particular case, what are the representative properties of the compacted aggregates? That's a big question mark. Now, bear in mind, what we are doing here is a back analysis. Okay, we are doing a back analysis, which means we are given the requirement to find out what is actually happening. It's like a forensic engineering, okay? And this is very much different from design, because design, you are starting from a white piece of paper. You are starting from literature. You are starting from whatever document design. So in this particular case, if you have designed stone columns, you know that using the Preby method, okay, probably you would start to design your stone columns using C dash equals to 0 and using your phi dash equals to 40. And in a lot of design procedure for stone columns, that's what you are recommended to do. So you start the design with C dash equals to 0, phi dash equals to 40, and then you carry through your design and it tells you how deep should this be, what is the capacity, what is the excess water pressure generated, what could be the settlement that you get in the end. But all this is design. Okay, so for our work here, we are doing back analysis. It's more than design. Later on, I will show you the results of what the back analysis says. It actually shows that the aggregates that you compact with high energy would actually be better characterized by the dilation angle. Okay, and with the dilation angle coming into the picture, you can actually mimic and represent the source structure behavior more correctly. Okay, so this is what I talk about in this paper. So if you some key discussion points in the subsequent slides. Why is this not changing? Okay, here. Okay, so the floating stone columns have been installed. We actually cast a capping beam over the columns, and then we use the cannelage load or the dead weight of your concrete blocks and to be jacked against your stone columns that has been installed. As you can see, the hydraulic jacks. Okay, so in this case here, the direct shear test result shows that you got a pretty obvious pause peak, a lot of interlocking going on. And then again, if you were to blow up actually this slide, you can see that non-linearity actually prevails as well. And then we have AB parameters, as you can see there. For tests, different types of tests. Okay, you got the AB parameters for macrotonalite, and then we will be able to fit a non-linear curve to it, and then we anticipate the confining pressure to be about 200. Okay, and then from there we will be able to get the C dash T and the phi dash T to represent the soil sample. Okay, so again we apply the power law, the generalized tangential method, like what we did previously. Now this plot here is very, very important, that describes the soil structure interaction behavior. Now I'm going to lead you through this, and right there is actually the response of the ground. Now I'm just trying to close this thing. I can't see how this box is like. It's got this box here, right? It's blocking my screen.
Yeah, to us it's not visible. To us, your screen is full.
Yeah, so that's just trying to get this box my way so that I will be able to see the screen better. Just bear with me a bit. Okay, so the figures here actually shows the load settlement response And the one in dotted line is actually the lot settlement response of what is actually measured in field. And then with all the other solid lines with different symbols, they are the ones that we did the parametric study. So we started with 5-S25, and we also recommend the back analysis actually recommends that we consider dilation. So dilation is actually, the equation is given as friction angle minus 30 degrees. And this 30 degrees is actually empirical, okay? And it's a function of your friction angle. So if we have that idea in mind, so if we have 25 degrees, okay, obviously the dilation angle is going to be 0, and the various lines there shows the various cohesion values, how it is, okay, in order to match back whatever that you have measured on site. So at friction angle 25, you see that is way off. Friction angles at a 30, okay, your settlement gets smaller and is approaching the dotted line. And then at friction angle as 35, now the dilation angle would actually appear, and then you see that settlement is reduced. Now we try friction angle of 40 degrees, and dilation angle is 10 degrees. We are, closing the gap between whatever that's back analyzed and whatever that's predicted, whatever that's measured on the ground. So if we try 45, it's getting better. So finally, we adopted friction angle of 50 degrees and a dilation angle of 20 degrees to be the most representative. And do bear in mind that this is 50 degrees friction angle and dilation angle of 20 degrees is what we use to back analyze 4 other case studies. And I'm just actually showing you only one. So we have been consistently using friction angle of 50 and dilation angle as a 20 for all the other lot test results and for back analysis. And they actually show very good representation of the outcome. So you can actually see this in our paper, where I actually show most of the case studies that we actually back analyze consistently using 50 friction angle and dilation angle is 20. So we provided a bit of a discussion there on what we observed, because if you were to start from design, okay, you would actually go friction angle as 40, okay, and then you do not use dilation angle, and it's actually you know that when you install your stone columns, you are introducing a lot of high energy compaction. So that high energy compaction actually transform itself in a way to a stored energy, and that is actually, you can think of it as appearing in the dilation angle. That dilation angle is the one that provides us with the enhanced property of a compacted stone columns. So if you were to design at 40 degrees and C dash as 0, actually that's actually very conservative. So Keller has actually looked at it. Yes, they acknowledge that that's our starting point in design, but what's happening in the field, nobody knows until this paper comes out. You see, so basically, because of the energy that you introduce in compacting the material, you can afford to actually use a higher friction angle value and accompany it with a dilation angle value that you could actually use. So contractors love this because it has been verified on site that you can be a bit more aggressive, and this is the field performance. So this research is a back analysis and a field performance. So they like this work, which means in the design, they are conservative, fine. But if they want to in project bids, for example, they can actually try to use a bit of a higher friction angle to be more competitive in their work, for example. Okay, so now with that prompt reminds me to release the poll question number 2. To do that, close the poll for the first one.
Yeah. Could you show the results for poll 1? We are interested.
Okay, how do I do that? Results. Poll results. Okay, and then apply. Do you guys see it?
Yes. Okay, so it's divided between A and B. Not sure? Oh, yes, I have.
Yeah. Okay. Yeah. A and B seems to have more responses. Okay, that's good. I will end the first poll results, and I'll do a new one. And I will sit now. Do you get Ashish?
Yes, I see it.
Okay. Okay, that's good. So what I'll do,
We can request everyone to participate.
okay, is that I will go back to the slides here. Okay, all good. And now this is the part where I'm going to share our research journey with you, ongoing and future research. So since then, we have also developed the transparent shear box. We use this in teaching as well as for research. So we developed some teaching practices, and you can see our paper that was just published last year in journals of ASCE Journal of Materials in Civil Engineering, where we describe about the interpretation of geomaterial behavioring using PIV technology. So how we actually describe the interaction of the particles, okay, and how it actually relate to the generalized tangential approach that we have been talking about. So do Google that paper, or if you wish, just drop me an email. I can actually send it to you, or you can find in my ResearchGate. Just type Dominic Ong ResearchGate Griffith University. You should be able to see a lot of my publications there that you can actually download. Okay, nowadays we are doing numerical simulations. So instead of physically reconstituting the sample, we are going more and more fundamentals. We are looking into interaction of particle at the particulate level, and how we also model particle angularity, stiffness, and material surface roughness in obtaining friction angle. Yeah, so we also use discrete element modeling. We are going to purchase Itasca's particle flow code, a PFC, soon, because what we've been doing is using Yate as an open source software. It seems like language is a main challenge for us, and we would like to do a bit more testing rather than on the computer coding. So we are going to get that software soon. This is the discrete element model that we have developed. As you can see, these are all spherical granular material. It's very good for teaching because we can actually show students what's actually happening in the soil in the shear box. So students actually love this kind of a simulation, because otherwise they can't visualize it properly. So as you can see, it's a progression of our research. First, we started with PIV. PIV is static arrow, vector arrows, and now we are slowly going on to a DM simulation to enhance the experience. Okay, so we even nowadays, angular, subangular, sub-rounded, rounded, and try to shape is very important in discrete element modeling. You can see those two particles there on your left. They will actually generate very different behavior if you were to shear them. And ironically, those two particle shapes share the same volume. So can you imagine they are so different in roughness, they are so different in shape, but they share the same volume. So if you're defining your particles in terms of volume, then you have to be fully aware of the discrepancy that you may generate in terms of generating responses from your particle interaction. So we want to investigate this. So it's getting more and more fundamentals. We are also trying to introduce a clumping technique, as you can see, if you the outline there, if you got a particle shape of such, and then we are trying to clump many spheres within the particle shape, and then that will actually help us to quantify the accuracy of the work. And in this clumping technique, as you can see, we want to make it really as possible. Okay, we have been using a lot of geometry extraction work, and this is a surface geometry that this is one sand grain. We managed to scan to very high resolution so that we can use it in the discrete element modeling. Okay, so obviously we don't work by ourselves on all this high-end modeling. We have partners who actually support us in terms of computational power. So I would like to acknowledge Nectar Cloud, who has been and NCRIS, who has been really wonderful in supporting our research. We are trying out synthetic particles. Okay, we are trying to have a quality control in terms of having particles of known stiffness, for example. We do 3D printing of particles as well. Okay, we choose the right powder to use and so on. Okay, this is a 3D printing, how we actually design it. Okay, and we put it for printing. And actually, this is the outcome. We can see that we can print various of particles of different shapes and surface roughness. And it's very much dependent on the resolution of your 3D printing machine. We are also working on the Bayesian inference AI concept, artificial intelligence, in terms of getting the whatever data or that we've got previously to provide a bit of a training, and then for the whole system to be able to be trained and then be able to forward predict. Because previously we've been doing on back analysis, we've got so much data, we've got so much experience now. So now we want to do something that would enable us to do a bit of a forward prediction with probabilistic function. So that's when we choose Bayesian, because it has the confidence level, which makes it stands out as compared to other AI method. Okay, in conclusion, the power law and generalized tangential approach has served us very well in developing understanding for a lot of our source structure problems. We also looked at how particle shape has a significant impact on the shear strength of the granular material. We use extraction, we use high-end technology nowadays that's available in the university. Almost free for us, even though if we have to pay, it will be a nominal amount. So the I have to acknowledge the good, very, very good facilities by the university that provide us with all these quality materials for us to work on. So it helps us to contextualize our research outcome into teaching, and it aids a lot on visualization. So that is why this very fundamental research here in the last 12 years or so, actually 12 years is starting from when Chu has graduated. So even before that, I would say that this project probably started 15 years ago when Chu signed on to this project. So it has been quite a while since we done this, and now we are already onto new research areas on source structure interactions like recycled aggregates for pavement, fault ballast, fault railway ballast, or even stabilized subgrade, where, as you can see, they are all granular geomaterial, where we could rely on our past experience and research outcome to help us to help propel us forward. Okay, and also obviously like to thank all the companies who have been supporting us throughout our journey. And with that, I'd like to end my presentation. Thank you. So I would appreciate it if there's any questions that you want to ask. I'll be happy to actually answer them.
Thank you, Dr. Dominic. Okay, the floor is open for questions, please. We are just above time, but if there is any, we can still take up a question or two, please. So I think people can unmute themselves. I just need to check this out.
Yeah, I can see the chat box.
Yeah. Yeah. So in fact, I have a small question, Dominic, about that 3D printing. The resolution lot depends upon the quality. So the minimum I saw was 1.5 millimeter. Is that the minimum you can achieve, or you can still go down less than 1.5 millimeter?
Yep, that's right. Within the university, we could actually print, you're right, up to 1.5. Have to outsource anything that's smaller. And then it's reasonable for us to do anything that's smaller than 1.5. So we are still contemplating on our resources, whether we want to get somebody to print something that's smaller than 1.5 and test it, or we're just going to ignore testing anything lesser than 1.5, at least for us to start off this particular research. So we are actually contemplating on that because it involves time and resources, and with the pandemic situation, it does not help. So yeah, all these questions are in our mind. Good question. It's a challenge, yes.
And the second one was on the dilatancy angle. So
Yeah.
dilatancy angle, you kind of took a varying instead, but how far is it from, in case I have to,
Sorry, I got a bit of a, you got cut off a little
true
bit.
dilatancy. Okay,
Can you
no, yeah, can you hear me?
Okay, I can hear you now. Sorry, I couldn't hear previously.
Yeah, I was more into the value of dilatancy angle. So in fact, I think you went up to 15 degrees or slightly or more. Is that, to me, I mean, it seems it's on the higher side, or is it something which is quite a number which can be taken at least in terms of design?
Yeah, we have gone angle up to 50, and then if you minus 30, that's your dilation angle. So that gives you about 20. If you were to really think about the vibro that Keller would actually use to actually compact the granular material, there's a possibility that there's over compaction and a lot of compaction that goes on in the work to form the stone columns, you see. So in this particular case, the back analysis shows that it's about 20 degrees dilation angle for up to cobble, up to 60 millimeters. So if you were to compare to sand, yes, definitely sand, you can see some, but probably not as large. But in terms of cobbles, my gut feeling is that there's probably a possibility and the back analysis actually shows that. But then again, it's a function of how much energy did Keller introduce to the sand column. So on that particular trials, as you know, being contractors, they know that you are trial testing your piles, and you know that a lot of focus on these installed piles. So you probably want to over compact. Okay, but if this over compaction actually carries forward higher group of piles that have been installed, that's fine, that's representative, you see. But what we are saying here is that it's just based on what they've actually installed on those piles to be tested for back analysis. Those piles actually represent, in a way, we back analyze to represent this kind of values. Of course, if there's conservatism to be applied, I would suggest that you probably use somewhere lower, and then discuss with your contractor on quality control, because for every single stone column pile that's actually produced, you can actually see how much energy that's actually been introduced to individual pile. So that involves quality control on the site that you want to make. If, let's say, you want to design something to be worthy of those values, apply it exactly on site.
Okay, so I think we have two more questions on stone column itself. So being on the subject, you want me to read the question out, or you can read it and then answer both ways?
Okay. I'm looking at the three questions, so I'll go through the first one. What is the minimum depth of soil strata where stone columns can be economically used? Now, if you were to go to conventional design, I would say that 25 meters, you're probably pushing the limit for stone columns in soft clay. As basically, they worry about verticality because there are few projects in Malaysia that the contractor wants to be involved in that try to replace pile foundation as well. I remember that anything that's more than 25 meters of soft clays, the contractor in general, they give up. They do not want to do anything that's deeper than 25 meters for stone columns. Okay, so that's the my thought on it. How do you decide the depth and pattern of floating columns? Some are going to have less columns was going deeper. So I did not actually went into detail. If you were to go back to the slides, I just want to show you that there are various patterns that the contractor actually considered. That one there. You can see that there's short columns in between the long columns, and you can see columns of the same length but spaced very closely, and then you can see columns that are spaced very closely but slightly alternate different length. So the contractor, to start off with, they are also unsure. Okay, so that's when they wanted the university to help them to interpret and make sense out of all this testing. So I would say they also try to push their design limit, and the good thing is that they are happy to spend money to verify in full-scale tests before they choose the final pattern to actually implement throughout. So what I'll actually say, a long story short, is that they finally choose the T3 in terms of design that actually gives them the most, the best performance, as well as in terms of cost. Okay, so in the end, they actually adopted T3 because if you were to look at floating columns, there are not many people, not many contractors who dare to actually do floating columns. Like what I said, in Malaysia, when all those ports that they wanted to build, they rather to have the stone columns sitting on stiffer ground. But this project here is only one aspect of the performance, but there's another aspect in terms of the settlement performance, as well as the load carry capacity that we have actually extensively debate and then and also back analyze. So it's not so much found in this because of its constraint, but definitely is something that has been talked about in terms of overall performance, carry capacity, and confidence in achieving this. So it was actually carried out, and settlement, I would say, has been very well. I believe the settlement that was imposed by the client to the contractor is about 150 millimeters. So all this has been done with settlement about maximum, I think it's about 100, and they've achieved the design criteria. Okay, the next question. In case of spherical shape grain, what is the influence of coordinate number on strength parameters? May I know is the what do you mean by the coordination number? Are you
Yeah, I think Professor Mir is there. Mir, could you unmute? Are you able to unmute yourself and say what is the question? Yeah, I think muting
or you can actually just type.
Good afternoon, sir. Am I audible? Hello.
Yes, you are audible. Audible.
Good afternoon, sir. Sir, actually, my clarification is in a direct shear test, when the spherical coordinates are being put together, there will be a lot of gap in between them, and the coordination number also matters. Means number of spherical particles in contact to each other.
Yes, that's right. I see.
And the neighboring particles also. So then, how the strength will vary? Have you accomplished that research?
Yes, that is one of the main issue. Now I see what you mean by the coordination number is the point of contact of the grains. So in this particular case, in the modeling, that's what we are trying to achieve. And as you know, it's very difficult to do parametric studies on discrete element modeling because of the computational time that is needed. So we basically started with the spheres with all of them the same size, and then after that and then after that we move on to having a well-graded material, which means smaller size as well as medium-sized particles in contact. Obviously, the contact points are more, and of course, when you have more contact points, it actually gives you a greater strength parameters. So that is the influence in terms of the particle gradation in terms of your soil strength. So for uniform soil, because uniform sand, because all your particles are the same size, and then the point of contact is going to be much lesser than if you have a well-graded sand, for example. So with that as our starting point, we do some work on that, and then now we are moving ahead. Now we are not only looking at the spherical contact, we are looking at irregular contact, and that is where we have a lot of difficulties in providing the what you call the influence of coordination number, but it's actually just the point of contact. So irregular particle shapes is the more challenging one that we are currently trying to solve. I hope that's your question. Influence of the in generate strength parameters.
Okay, we just in time. I think it's just one, and it took. We just ending one in time. That was quite nice.
Thank you.
I don't see any more questions, but if there's anything, please do write to Professor Dominic. He's available over email.
Yep, I
If
will. I
it's
will
an
just. I'll just type my email here as well. If it's not anywhere, I think it's mentioned on the first slide. But in any case, I've got it there. D.Ong ONG at griffith.edu.au.
Yep. Thank you. Thank you very much, Professor Dominic.
Thank you, Ashish, for having me, and thank you to all the participants in staying with me for the last 1.5 hours. Appreciate it, and my pleasure to be sharing my experience with you. I rather call it sharing than being something that is forced onto you. But this is our experience, and I'm happy to share that. Thank you.